Solving systems of linear equations using row reduction and technology. So first is the good old-fashioned way for math 10. Solving those systems. Notice how these are two equations in two unknowns. So they represent two lines. So you're trying to see where they intersect. If they intersect in a point, if they don't intersect at all, or if they are the exact same line. Okay, so do that. You can use substitution or elimination. I'm going to use elimination, but you do that whatever way you see fit. Those three. Okay, then we're going to do what's called row reduction method, and then our calculator. Okay, so you would have found the first one has 1 point of intersection, so they crisscross. Second one, when you use elimination, you get 0 equals -4, which obviously it doesn't. So that's a no solutions. So you can write out no solutions or put the null set, means the set of no solutions. Here, when you use elimination, you get the left side equaling the right side. If you had done a different method, sometimes you might get 2 equals 2 or whatever it is, depending on how the equations are set up. But if this is true, then it doesn't matter what x or y are. They're always going to be on the same line. So there's infinitely many solutions. Solution set, you can just copy out one of the equations. So you could copy out kind of like with a positive x term. Okay, so that is the solution set, right? Anything that satisfies that. Now, because we're learning and continuing on with vectors, what we could do is show this in vector form. So what I'm going to do now is, you might not remember so much, but hopefully you remember a little bit. And then we're going to go into it next week in way more detail. So if we let, for example, we could let x be some parameter t, where t is a real number, okay? And then if we put that back in, so then we substitute that into the second equation, then we'll get -8y equals -4t minus 2, and solve for y. We get 1/2 t plus 1/4. Okay, so we can, these are called parametric equations. We just can show them like that. Okay, and then of course we can show that in vector form as well with our parameter t. We'll just leave that for now, because I said we're going to review all of that. But these are the parametric equations, where t is a real number. So that's another way of showing it. That's really not the point of today. Point of today is remembering how to solve a system. Okay, so that is algebraically. Take a look at the next one. It says use row reduction to solve the same system of equations. So what does row reduction mean? Basically, it's a form of elimination. That in your system, you want to reduce the system. Basically, there's the word in it, to be simpler. And so the normal steps for row reduction is that you can see here we have, the way this is set up is the constant term is always on the right of the equal sign. So in row reduction, we want to basically here make this 0. Okay, so we're going to have to use probably a multiple of both equations, add them and subtract them to get down to this entry underneath the first 2x to be 0. Okay, that's what your calculator will end up doing, and your calculator is going to be basically what you're going to use. Okay, but we're doing it the old-fashioned way. So we want to get rid of that x term by adding and subtracting those two equations. You're reducing the So basically, these are pretty small, but when we get to bigger ones, so if we have, this will be your matrix, but actually we wouldn't show it like that. If you take a look actually on the other side, then we've got 3 equations and 3 unknowns. So 3 and your equal sign. So basically, when we're row reducing, if we did this the long way, we're trying to make these, anything underneath the diagonal, 0. Because then you have something in terms of basically z equals a number, if there is a point of intersection, and move it back. So you're trying to add and subtract these equations, because remember, adding and subtracting doesn't change anything. Over here, we multiplied this by number, so it doesn't change the system, right? As long as you keep and multiply both sides by the same number, still the same equation, okay? We can add them or subtract them. That helps you solve your system. So as long as you treat every part of each equation equally and add and subtract every part, you're not changing the system. So here for row reduction, I'm just going to keep the first one the same, okay? And then I'm going to call this row 1 and row 2. So if I want to get this to be 0, okay, I want to, basically, I need the same coefficients here. So I would take 2 times row 2 and subtract 3 times row 1. Okay, or you could go 3 times row 1, subtract 2 times row 2. This is, so if I do this, I go 2 times row 2, so 3 times 2 is 6x, minus 3 times 2x is 6x, so that's 0. Same thing for the next. So 2 times -1 is -2, minus -2y, minus 3y is minus 5y. And then 22 minus 27 is -5. Just going to move this. Okay. Now I can finish that off, right? Now I've got a 0 there. You could divide both sides by -5, but really now I'm solving this. -5y equals -5, so y equals 1. Then substitute back in to the other equation. And I get the same solution. Okay, so it's basically a form of elimination. But it's really called row reduction, where you're trying to make every entry underneath the first one 0 in the first column, and then diagonally from there. All right, if you were doing a 3 by 3. If this was, say we had a 4 by 4 here, then I would be wanting my diagonal. It would be everything here. I'd want to be 0s. In the old days, when I was young, I had to do this by hand. Then we got to use a computer with a floppy disk, a floppy, big, that actually were floppy. And that was our matrix solution problem in university or program. So you went to the computer, plugged it in, solved the system. That was exciting. Okay, so the next one, same kind of deal here. So this is R1, this is R2. So you can leave the first one. And then how do you get this entry to be 0? Well, you could take R2 and add 2 times R1. Second row, add 2 times this would be 0. Second row, add 2 times 2y is 4y. That's going to be 0. This 2 times this is -4. And so that right, is not possible. So no solutions. I guess here I should go to 4. And then here, when you do the same thing, then so I'm just going to copy up the first one. And so the second one, I can do R2 plus 2 times R1. R2 plus 2 times R1. R2 plus 2 times R1. And again, I like to use the one that doesn't have a negative coefficient just because it's nicer. Now, saying that, I should probably, you can also reduce that, right? So 2x, so the positive version. Any version. Yep. That's what I said, yeah. So it's called row reduction when you're making that first entry 0. That's just what row reduction is. Yeah. Absolutely it is. Well, usually when we use elimination, we don't do that. So this is the first step to doing the full thing where you're making each row, as I showed you. It's called row reduction when you're making those zeros. Pardon? Oh, absolutely. Yeah. Yeah, but the point is to know what this is. You're going to use elimination, right? But this, we don't want to start with a 4x4 and do row reduction. As I said, you're going to use your calculator to do these. I'm showing you what it is so you understand what your calculator is doing. Okay, so you might have to do just a little bit of work, right? And then you're going to use your calculator. You can handle it. You can. So, graphing calculator. Now we get into our calculators. Okay. So, in your calculator, you may have used these before, but matrix. So, second x to the negative 1 is matrix. We need to edit because we need to create one. Okay. If your calculator, you probably haven't used a matrix for a long time if you have it all. And so this is probably empty. If you reset, every time you reset, it clears them. So enter on A. You have to tell it the size of your matrix. So the first entry is the number of rows, so 2. And the number of columns is 3. Okay. If it's 2 unknowns, there could be 3 columns because there's got to be a constant. Okay, and you can check, right? It'll show up. Just make sure you put 3 by 2, it'll look different. Then you just enter. So here you're looking at the coefficients, and when I write it out on paper, I put a line for where the equal sign is, but this is 2, 1, 9, 3, negative 1, 11. So 2. You can just enter after each entry. You don't have to even cursor. And it'll go every row, and it'll go to the right. Okay, so we've done all the entries. Then we'll quit out of that. So then we have to do some, get the calculator to do our work. So go back to matrix. And then now we're going to do some math with it. So if you cursor, you can cursor down or cursor up is a little bit faster. So you'll see these A and B. You see REF, ref, and RREF. So ref, and I call it ref. So, not too much. In any case, if we do REF, let's do that first. So enter on that. Tell it which matrix. So second matrix, just enter on A or whatever one it's in. Okay. It makes that first entry underneath 0, but it also makes the diagonals 1. So that's what we didn't do. So we just did the first step of row reduction. Now the E there means row echelon form. So row echelon form has 1s here. Okay. Row reduced echelon form, or ref, the 2 R's, will have 0s above the diagonals, if possible. So now looking at this, I can solve, now I know that, that here, y is 1, put that back in. Now those are decimals. If you want to convert it to fraction, what's the fast way? I think, no, that's not what I want to do. I want to, oh yeah, sorry, math frac. So take that answer and it'll convert it to fraction form for you. Okay. So this, if I were doing this on a test, I'd say row echelon form with an arrow, 1, -1/3, 11/3, 0, 1, 1. Then from there, I go, okay, y equals 1. And then my substitution gives me x equals 12/3, which is 4. Okay, now let's do the same thing with ref. So math, oh sorry, not math. Second x to the -1, which is matrix, math, so different math key. Then you can just go up, it's a little bit faster. And then for my matrix A, okay, and that will actually solve all the way. So here the diagonals are 1 of the square matrix that's got the variables. And then these opposite diagonals are 0, right? So that is the fastest way to get your solution, is RREF. Okay, so if you do RREF, you put RREF and then put your matrix there. Okay, so you do the next one, see what it looks like when you use that in the calculator. Because we know one is no solutions, the next one is no solutions, and the one after that is infinitely many. So you can just change the first one because they're very similar, right? So, okay, so -1. Did you sign out? Yeah, I signed out. Oh, actually, this one and this one, they're similar. Just change those. And then so if you do row reduced echelon form of matrix A, so row reduced echelon form, so before we had 0 equals 4 or -4, which isn't true. Here it's 0 equals 1, not true. Okay, doesn't matter what that value is. So this is not possible. No solutions. Okay, so remember that's your equal sign. So 0 cannot equal 1. Okay, so from that, 0 does equal 0, so same. Okay, these are the same questions. Just using a calculator. Okay, so just do an arrow and tell me are you doing row reduced, echelon form, row echelon form. Okay, so next one. Use row reduction to solve the system of equations in part A, and then use your calculator to solve the rest. So we're doing 1 the long, old-fashioned way. Okay, but you can use the matrix form, so you're not writing out X, Y, and Z all the time. So here, you can write it out in matrix form, but then use your row reduction. Okay, so this, call this R1, R2, R3. Then next step is to make these zeros. Now what you can do is make this 1 to start. You can go all the way, but I'm not asking you. Just as row reduction, not row echelon form where it has to be 1s, not row reduced echelon form, which it has to be 1s, 0s, and 0s there. So basically, I'm just asking you to make these zeros. Okay? So on a test, I might ask you, given something like this, do row reduction on 2, right? Tell me what you're doing. Yep.
And you have to write down the R already.
Yep. Okay, but that's about it. The rest you'll use your calculator for. Okay. So copy out your first row. Then here, to get this to be 0, you can take this and subtract 2 times this and put it in, or you can take this times 2 and subtract this. I tend to always start with the row that I'm wanting to replace. So this one here, I would go 2R2, subtract R1. So that's going to be 0. -4 minus 1 is -5. 6 minus -1 is 7. 14 minus 2 is 12. Now what you could do for this next one, rather than going 2 times this minus 3 times this, you can use this row as well. So you could go R3 minus 3R2. So 3 minus 3 is 0. 5 minus 3 times 2, so that's adding 6, is 11. Negative 3, that's right, negative 1 minus 9 is negative 10. And 0 minus 21 is negative 21. Now, from here, got to make this 0. And the problem is, if you use the first row, then you're going to end up with a number here. Okay, so really you want to compare it to the second row. Okay, so this one would be 2, 1, 1, 2. So now this is our new R1 and R2 and R3. Okay, so okay, so we'd have to, is that me? No. 5 times this plus 11 times R2. So 55 plus 55 is 0. Negative 50 plus, so negative 50 plus 77 is 27. 5, so that's negative 105. Plus 132, which is 27. Okay, so therefore 27 Z equals 27. So Z equals 1. And negative 5Y plus 7 times 1 equals 12. All right, so then for the rest of them, you can use your calculator. And then for the last one, just take a look at the last one there. EEF says write your answer in terms of K. So that one you might, you're going to need to use the method that we just did. Can't put K into your calculator. And then think about what values of K would give you certain solutions. Okay? When would you get one pointed solution? When would you get no solutions? When would you get infinitely many solutions? Okay? So, leaving that for you to do on your calculator. So for that second one, just notice how I show it at the end. So that's 2 equations in 3 unknowns. And so this is as far as you can get. So let Z be a parameter, and then T. So T can be any real number. And that means Y is negative 5T plus 5, X is 17 minus 4, and you can show it like that. So really, what that represents in terms of vectors, etc., is really a Cartesian equation in 3 variables represent the equation of a plane. So a plane is like a piece of paper like this. So that's the intersection of two pieces of paper. Okay, and so here, this represents the line of intersection where that other piece of paper is intersecting. Okay, so it's an infinite number of solutions, but it has to follow a certain line of intersection. We'll talk way more about that next week, but that's how I would show the solution. Okay, because it's not a square matrix; it cannot be a point. Okay, so no solutions for C. Okay, so in D, enter that row reduced echelon form. You get the bottom row of zeros, so it means there are infinitely many solutions. What is the solution? So again, we're going to talk more about this, but three planes intersecting, infinitely many solutions. So they could be all the same plane, but that would end up with two rows of zeros because it's just the same equation of the line. This case would be could be two parallel and one through it to get a line, but none of those are parallel. They're not scalar multiples. So this is like a book. The pages in a book. So if that's there, these are like this. So they meet in a line. So it's an infinite number of solutions meeting in a line. So again, same thing. Let, in this case, Z be a parameter. Now, a little hint on this one is if these are fractions, you can let Z be a parameter, T. You can let it be 5T, 2.23, like it can be a fraction as well. But if I let this be 5T, then I don't have fractions. Is it wrong to do it just T? Nope. Because you'll see the direction vector, again, when we review vectors. So if I let it be 5T, then I'll have Y minus 3/5 times 5T equals 0. So the 5's divide out. So I get Y equals 3T. Then if I then I'll have X plus 2/5 times 5T equals 0. 5's divide out, so I get X equals negative 2T. Good. What did I do? Oh, equals to 2. Right, sorry. Equals to 2. So negative 2T plus 2. So then you can just summarize that. Oh, look at that. Summarize that. So here, this produces the last two lines are 0, so infinitely many solutions. If you take a look back, these are all multiples of each other. So you know it's the exact same thing, exact same equation. These are representing planes, so they are exactly the same plane, so they intersect an infinite number of points, and you can just choose one of those equations as your solution. We will look at vector forms of the equation of a plane. So kind of like this form, but that'll be next week. So we'll just leave it like this. You could let Z be a parameter, Y be a parameter, and that would get you the vector equation, but as I said, we're going to do that next week. Have an unknown. You're doing this by hand because you can't put it into your calculator. Get down here, so you're trying to make these zeros, which we did. Turns out this ends up being 0. And so this is K minus 5. So there'll be infinitely many solutions if K minus 5 is 0, so that means K is 5. Solution to that gets a little bit messy here, but you could now, if K is 5, put that back into your original matrix and use your calculator. That's probably the easiest, because this ends up a lot of substitution. You can certainly do it, you're capable of. So
So, or use out with k equals 5. Okay. Now, if k is not 5, what happens? No solutions. If there was a number here, it would be different, right? So if k is not equal to 5, there's no solutions. If k is 5, so now let's get our calculator out. And it's a 3, 4, and it's not. So, 2, 1, so then, we go here. Minus 30, so y then would be equal to negative 1 minus 11t, so x would equal negative 1 minus 10t. So, in this solution, is